we have 39 grams of KO2, or potassium superoxide, that reacts at 25 degrees Celsius with carbon dioxide that is kept in a 3.3 liter sealed vessel with an original pressure of 6.4 atmospheres. We are asked what is the total final pressure of the system after completion of the reaction, and we're given that we can assume the temperature is constant and that the volume occupied by the solids is negligible. So the first thing that I really want to emphasize here is the fact that they say the volume occupied by the solids is negligible. So this actually allows us to use the ideal gas law, and that's really key for this problem. Because the way we can find the total pressure of this system is actually based on how many moles of gas this reaction produced that we're given below here. And so we're going to do some calculations to find that out, and then eventually use the ideal gas law to find the final pressure of the system. So the first thing that we need to do is find the amount of gas at the end of the reaction. That's what is producing that pressure. So in order to do that, we need to find if there is any left over carbon dioxide, because we know we're producing oxygen, that's a given, but we don't know if carbon dioxide is our limiting reactant or not, because if it's not, we're actually going to have some excess carbon dioxide at the end of the reaction that also contributes to the pressure. So to do that, let's start with finding the initial amount of KO2 and CO2. So we can use the ideal gas law to find initial moles of CO2, or carbon dioxide. And so I'm just going to set this up, PV equals nRT, and in our form we want it as N equals PV over RT to find the number of moles. And that equals 6.4 atmospheres, our original pressure, times 3.3 liters, which is the volume of our vessel we were given, and then divided by our gas constant, and our temperature is in Kelvin. So now that we have that, I get that we have 0.863 moles of carbon dioxide at the beginning of the reaction. So now we can find the moles of KO2 at the beginning of reaction. And we were actually given that we have 39 grams of it. So using that information and the molar mass, we can figure out how many moles we start with. So we're going to take our 39 grams and use the molar mass to get 0.549 moles of KO2. And so now that we do that, we can find the limiting reactant, and if you have a different way of doing that, definitely keep doing what you're doing, but this is usually how I do the limiting reactant problems. So we're going to find the limiting reactant. So what I do is just pick an arbitrary reactant. So I'll pick KO2 in this case, and I'm going to convert this to our other reactant, which is carbon dioxide. So this is just based on the stoichiometric coefficients in our balanced equation above, and this is really similar to what you did in the first exam. So for every 4 moles of KO2, we have 2 moles of carbon dioxide, and I get 0.2745 moles of carbon dioxide. So to react all of my KO2, I need 0.2745 moles of carbon dioxide. Well, we calculated above that we actually have 0.863 moles of carbon dioxide. So we have more than enough. So that means that KO2 is limiting, or potassium superoxide. Okay, so now that we know that CO2 is in excess, we do have some present at the end of the reaction. So to find the amount left over, I'm going to take the initial amount that we found, which is 0.863 moles, subtract the 0.2745 moles that we need to completely react KO2, and I get 0.5885 moles of carbon dioxide that are left over. So we have that, and now we know that oxygen is being produced, and oxygen is contributing to that final pressure. So let's find the amount of moles of oxygen produced. And this depends on our limiting reactant. So we can start with our limiting reactant, which we found was KO2 again, and just use the fact that for every 4 moles of KO2, 3 moles of oxygen are produced, and we get 0.412 moles of oxygen are produced in total. So now we can figure out the total gas left over at the end of the reaction. So I just add the 0.412 moles of oxygen plus the 0.5885 moles of carbon dioxide that's left over to get 1.005 moles of gas in total at the end of our reaction. So now that we have that, we can go to our final step, which is finding the final pressure. And we can use the ideal gas law for this. So we know that P equals nRT over our volume. We know that N equals 1.005 moles. Our R is 0.0821 liter atmospheres per mole Kelvin. And we have our temperature. We're told that it remains constant in the problem statement. And I converted it to Kelvin. And then I'm going to divide by our volume, which is 3.3 liters. And I end up getting that the final pressure is 7.4 atmospheres.